All right, so we've talked about the basics of integration as far as antiderivatives are concerned, and we've seen how to evaluate an indefinite integral. Now we're going to evaluate a definite integral. And so for this example, when we say integrate the following, the integral of x cubed plus 2 from -2 to 2, what we are actually talking about doing here is we want to figure out what is the area under the curve, or what is the sum of all this area here. So we got this part plus all of this here. And so without me trying to get too colorful with it, we want to figure out what the sum of all this area is. Now, one of the things that we assume here is that anything that is above the x-axis, we count that as being positive. And anything that is below the x-axis, we count that as being negative. Okay? So you'll see that when we actually evaluate this integral here, we're going to have a positive portion and a negative portion. And so the negative portion will refer to this portion of the area here, and the positive part will refer to this portion here. All right, so let's go ahead and get started. So when we do this, the first thing that we note is that we have two functions added to each other. And so we know how to deal with the integral of a power function, and the way that we deal with the integral of a constant is that we have to remember that if we have a constant, that's the same as having that constant multiplied by 1. And we can look at 1 as x to the power of 0. Now, if we were to use the power function method for doing the integral, then we would have to say plus 1 here over 0 plus 1 there. And you see we would end up just getting this, but it would just be 2x. So the easy way to think about this is that whenever you have a constant and you need to integrate it, it just goes back to what that constant is times x. And this makes sense because if we were trying to take the derivative of the function or the line 2x, we know that the derivative stands for the slope, and the slope of that line is 2. And so if we went backwards from here to here and say, give me the integral of, or the antiderivative of, a line that has a slope of 2. And so here that would be 2x plus b. And b would be whatever the y-intercept would be. Okay? So that's why that makes sense. So we'll go ahead and erase all of this, and then afterwards complete the example. All right. So here, I'm going to rewrite this. And this would equal, for this portion, we say x to the 3 plus 1 over 3 plus 1. And for this portion here, this would just be 2 to the x. And watch how I do this. We're going to take this and evaluate it from -2 to 2. So here we're saying, hey, I'm going to look at the area under this particular curve from when x is -2 to when x is 2 here. Okay? And so for those of you that can't see that, we want to study the area under the curve from here all the way to here. Okay? And so we're going to figure out this portion, and we're going to figure out this portion. So we clean this up, and we'll see here that we get x to the fourth over 4, or 1/4 x to the fourth. Seems like, okay, plus 2x. Now again, we're going to say we're evaluating that from -2 to 2. And so how we do that is we're going to plug in 2 into this and then subtract it from when we plug in -2. So that's the way that we go about evaluating definite integrals. So first go round, you'll see that we will plug in a 2. So it'll be 2 to the 4th power over 4 plus 2 times 2. And then we say minus, and now we plug in a -2 into the function. Okay, and so now from this point, this is just evaluation here. So this is 2 to the 4th power. I know that looks kind of funny, so I'm going to try to fix that. Try to write that again. So 2 to the 4th power is 16. 16 divided by 4 is 4. See, my marker doesn't want to work well with me today. That's all right. We'll keep moving along. So we know we have 4 right here, and then we know 2 plus 2 is 4. Minus, here this is a 4. So we have 16 divided by 4 is 4. And then here we have minus 4. And so of course this part just ends up being 0. So what we have left is 8. And so since we don't have any units to go by, we say that this is going to be 8 square units if we're looking at it geometrically. Okay. So again, when we take the definite integral, we do the antiderivative, and then we evaluate the antiderivative at the endpoints of the x values that we chose here. And we have this portion plus this portion. Okay. All right, so the final example that we'll have here is we'll do an application problem where we look at the marginal cost of a particular function, and then we want to figure out the total cost. So that'll be our next example, next and final example.